Good morning. I'm going to give you guys about 7 minutes to go through these problems, and then we will go through them together. Good morning. All right. I'm going to draw these out on a separate page just to give a little bit more room to talk through these. So first two are alkylation products. Sodium hydride, NaH, is going to be considered a small base. We're going to follow this up with propyl iodide. So our small base should make our enolate on our more substituted position, which means it's going to be pulling off this proton here. Giving us this enolate. Our enolate can then attack doing an SN2 at this iodide center here. And adding our 3-carbon unit to our product. All right, our second problem here, we are dealing with LDA, which is going to be a large base. Which means that we're going to be pulling off one of these two less substituted protons in order to get our enolate. Should look something like this here. From this point, we drew ethyl bromide as our electrophile. So doing that nucleophilic attack, these can be shifted over. And we can get our less substituted product in this case. All right, our next problem is going to be a Claisen condensation. We are taking this ethyl ester here, adding in sodium methoxide. We can generate an enolate. Oops. these electrons can be shifted downward. We can attack this other version of our starting material here. We'll form this negatively charged adduct here. The electrons from our oxygen can come down, form a carbonyl, kick out this OET, and we can make our final product. Which should look something like this. All right, let's move on to the cyclic version. I'm going to give you guys some advice for how to do these. We didn't really talk about them much on Wednesday. We talked about them with aldols. We didn't talk about them with clazins. It's kind of the same concept. I'm going to kind of walk you through a strategy for doing them, though, which I think will be helpful. So let's get started on it. All right, so there are two products to this, as I indicated. Let's talk about just the first one. Second one, if you can make the first one, the second one's gonna be really easy to make. So this is not symmetrical. There are two different sets of protons here, which can be pulled off. Let's start with the ones on the left. So if I pull these off, make our enolate. Should look like this here. And then we're going to have these electrons come down, attack, and we're going to make a ring. The size of the ring is going to be the end of this enolate here. So this would be carbon 1, 2, 3, 4, 5 here. So the easiest way to do these is just to start off by drawing this ring. So we said it's going to be a 5-membered ring. Let's draw a 5-membered ring. Let's number them. Pick a spot to start. 1, 2, 3, 4, 5 here. So carbon 2 had these two methyls coming off of them. We can start with that. Carbon 5 had our oxygen and our OET. So we can draw our O and our OET. Carbon 1 has this ester coming off of it. And that gets us to our structure. From here, we're just doing the normal thing. Electrons come down. We kick out an OET, and we get to our product. Okay, so for making the other product, so if we pull off these other protons here, make the other enolate, oh, I didn't make that into an enolate. Okay, so should just be a single bond here, double bond there. The easiest way to make this into your product, and it'll let you do exactly what you did before, is to just rotate this clockwise 180 degrees so it lines up with how this was. So if we take this and we just pick it up, turn it over, it'll look so we'll have our negative here with our double bond. We have 1, 2, 3, 1, 2, 3. OET. This is really nice because this is almost identical to what we have up here. The only difference is we shifted these two methyl groups. So now when we do our cyclization, we have 1, 2, 3, 4, 5. It's going to look almost identical. The only real difference is that on carbon 3, we have those two ethyl groups. And then from here, these two electrons can come down, kick out the OAT, and we'll make our product. Oops. So this is a way to kind of simplify. If you made the ring right the first time, you should be able to make it right the second time. You're just going to have to shift where like those small groups are. All right, last problem. Also a ring closing. This one's honestly a little simpler because you're only going to have one product. We have an aldehyde and a ketone on the same structure. Oof. Aldehyde is more acidic, which means that that is the structure that's going to make our enolate. So these protons here are more acidic than the pairs from our ketone. So we will generate just this one. Enolate here. Our electrons can do an attack. Like before, this is going to make a 1, 2, 3, 4, 5-membered ring. If I number my ring, 1, 2, 3, 4, 5 here. On 3, I had these two methyls. 1, I had the aldehyde. On 5, I have the O minus, which we can add an extra oxygen or proton to in a minute. So this gets me to my O minus. I can pick up a proton. First step, we made water, so we can just grab a proton from that. And then from here, using heat, we can eliminate it to make our double bond. I still on the giving us this product. All right, so today we are going to talk through a good amount of 21. We'll probably finish it on Monday. Wednesday we'll do a little of 22. 22 is just making amines, which we've kind of been learning this entire time. So it's really just a big review. You know how to make them already. So let's talk about finishing up the Claisen reaction. We just did the intramolecular one. We're making the cyclic forms. The other one we didn't really talk about is a cross Claisen, which is going to be very similar to the cross aldol reaction. If I take two different esters, add them together, and sodium ethoxide, because we have an OET here. What we can do is, again, we're going to get 4 products. So each of these is going to have 2 pathways that can go down. So it'll make an enolate. It's going to look the same for both of them. At this point, this can either interact with itself. So let's start with that. So if this interacts with itself, going to form a bond, kick these electrons up, eventually kick them back down and kick this out here. We are going to make something that looks like our original structure with attached to where this OET was as now this ketone here. All right. This can also interact with our other starting material. So we're going to do almost the exact same reaction. The only difference is that over here, we had an ethyl off of it versus over here, we only have a methyl. So our product should be almost exactly the same. The difference is between having an ethyl here versus just having a methyl. The product from this should look like this, where we just lost this methyl group here. All right, our other ester here can form the same enolate twice. From this point, we can either interact with another equivalent of our first starting material. So looking at this reaction here versus this reaction here, the difference is a methyl group. I don't have that methyl group over here. So this methyl here equated to this methyl in the product. So my product should be identical except deleting that group there. And then for my final over here, I should interact with another equivalent of the second starting material. These two reactions are almost identical. We just deleted off this carbon here, which we equated to this one. So I should get this product from my reaction. Okay. So let's talk about malonic acid synthesis. Malonic acid synthesis. Oof, mouthful. So back in chapter 20, we talked about a reaction. It was just a Grignard reaction. You could take ethyl bromide here, throw in magnesium chloride, or not magnesium, just magnesium, and CO2 and H3O plus. And when you did all of that, you ended up generating this carboxylic acid. And what's interesting about this carboxylic acid is that we added a carbon to it. We started out with ethyl bromide and we ended up with propanoic acid. So we've extended to one carbon. Today we're going to be doing what's called the malonic acid synthesis. And unlike this reaction here, so let's redraw it. And I'll go through each of these steps in a minute. I'm just going to kind of give you an overview. We're going to add diethyl malonate that's been deprotonated. As well as H3O plus and heat. What this is going to end up forming is butanoic acid. So this is going to let us add 2 carbons. So the way this malonic acid synthesis works is we're going to start with diethylmalonate. Which looks like this here. If we add in our normal base, so these are ethyls, we're going to use sodium methoxide. We talked about these pretty early on. These have a pKa of about 13 here. They're very acidic. So it's pretty easy to pull one of these off. You could technically make an enolate. I'm going to draw the resonance structure where the negative charge is here, just because that's where all the chemistry is going to be happening. From this point in time, if I add in ethyl bromide, I can do an SN2. From here, we're going to add an H3O plus. So that was a reaction we learned in chapter 20. If you add an H3O plus with an ester, you can make a carboxylic acid back. A lot of steps, and I'm not going to go over it. And then from this point, we're going to do what's called a decarboxylation, which is where you add in heat. And I'm not really going to talk about specifically what happens, but basically we're going to lose one of these these carboxylates. It's going to turn into CO2. So I'm going to do the one on the left. It's symmetrical. It doesn't matter if you do the one on the right here. But if we were to lose this as CO2, helps if the marker's opened. We can get our product. So sum these up into kind of one step, or well, really 3 steps. Starting with diethylmalonate. Throwing in NaOET, followed by, let's do a different file this time. Let's do iodopropane. And then our third thing is going to be H3O plus and heat here. I'm just going to kind of chunk it. So our first part would give us this malonate with this propyl group on here. At this point, we're going to lose these into carboxylic acids. We're going to eliminate one of these CO2s to form a carboxylic acid. Any questions in a while? All right, so there's 2 protons on there, so we can take a look at this twice. Talk through that. In this first step here, there's 2 protons on this diethyl malonate. Which means if I add in NaOET followed by ethyl bromide, I can add the ethyl group. And I still have another proton on there, which means I can do it again. So I can add something different. So if this is all one thing, you could make this 3. So NaOET, I don't know, like this. This is going to let us dialkylate. Giving us this product here. Our last step would be H3O plus and water, or sorry, H3O plus is water, and heat here. It'll let us remove one of these 2. Let's see, I want to draw this. To give us this product. So we lost this group in the decarboxylation, and that transformed into, this other one transformed into a carboxylic acid. All right, so that is the double alkylation. Let's see. So we just did diethyl malonate. We can do something very similar. This is a diethyl malonate. And that's going to be with what's called acetoacetic acid, which is kind of a mouthful also. And that's going to look like this. So basically just removed this ester here, replaced it with a ketone. Sorry, remove this ester here, replaced it with a ketone. And when we do our decarboxylation, as opposed to having 2 options, we're only going to have 1. But it's going to follow the exact same principles. I don't like this marker as much. So our acetoacetic acid we can throw in NaOET followed by some sort of electrophile, H3O plus, and heat here. It's going to let us generate originally. So from our deprotonation alkylation, we'll get to here, adding an H3O plus, will let us remove this ester into a carboxylic acid. And then heat will let us decarboxylate. To form our ketone. Oops. Like with the malonic acid synthesis, I have two different protons down here. So we could technically do it twice. I want to write it out in one step. So we'd have Na OET. Oops. We could add in, let's add in ethyl bromide. We could add in NaOET again. And let's do propyl bromide. And then in our last step, H3O plus and heat. So these are all 5 steps done at once. We're going to alkylate once with this ethyl group here, alkylate again with our propyl. We'll end up losing. So creating a carboxylic acid and then losing it. We're going to be left with just basically acetone here. So let's start out with just drawing acetone. We added a ethyl to it and a propyl to it. And that's going to be your final product. All right, I'm going to talk about one last reaction for today, just to kind of start the concept we're going to talk about on Monday, which is Michael additions. It's a pretty straightforward concept. If I have an alpha beta unsaturated ketone, which is kind of what we've been doing with our aldol reaction. So this here, which is a common product from these aldol reactions, if I was to add in a Grignard is a pretty harsh alkylating reagent. It's going to do probably what you expect it to do. It'll attack this ketone. We're going to make an alcohol out of it. Add this ethyl bromide here. If instead we want to do what's called a Michael addition, we're going to need a softer alkylating reagent, which we've already used back when we were doing acid chlorides. So if I add in lithium, copper, LiCu, we added ethyl here, so Et, followed by H3O plus. What I can have happen is this ethyl minus that we created. I'm just going to draw it as an Et. I don't want to draw out the whole complex. These electrons can do an attack on this beta center instead of directly attaching the carbonyl like it did over here. This is going to kick our electrons all the way up to our carbonyl. And then we can reprotonate. So reform our carbonyl, grab an H+, to form this, what's called Michael addition product. So up here, we added this allyl group directly to our carbonyl, versus over here, we added it through the conjugated system. So we attacked at this beta position, which then we were able to reform our carbonyl and form this other adduct here. So on Monday, we're to talk through a bunch of different reactions that deal with these. And then on Wednesday, we'll probably cover a little bit of chapter 22, and that should be all the material in the course. So I will see you guys on Monday.